Hi friends, welcome to Ec&Ps. Now we will discuss about GATE 2016 question paper for electrical department on the topic of electric circuits and power electronics. Now we will see one by one. The first problem is a transistor circuit is below. The zener diode breakdown voltage is 5.3 volt. Take base to emitter voltage drop to be 0.6 volt. The value of current gain beta is. So we want to calculate beta value. So they were provided zener diode breakdown voltage 5.3 volt and base to emitter voltage drop VBE is 0.6 volt. So we want to calculate beta voltage current gain of transistor beta. So from this diagram, so we want to calculate one by one. So first apply KCL at base point. So for base point, so here, so what is the function of base point applied here means point minus 5.3 volt plus 0.6 volt plus IE into 0.47 into alpha is equal to 0. That is 0.472 into equal to 0. So for this case we want to rewrite IE value. So IE is equal to 10 milliamps from this equation. Then apply KCL through supply 4.7 kilo ohm. So apply through this also. So for this consideration we want to move to resistor and diode value. So minus 10 plus I into 4.7 plus 5.3 equal to 0. For this case I is equal to 1 milliamps. So from the figure IB is equal to, that is this one, from the figure IB is equal to, here IB is equal to I minus 0.5 milliamps. So this current I minus 0.5 milliamps. So I value is 1 milliamps, 0.5 will be reduced, means IB is equal to 0.5 milliamps. Then IC, we know about the IC. IC is equal to IE minus IB value. IE is 10, then IB is 0.5, then IC is equal to 9.5 milliamps. So for current gain formula is IC divided by IB. So IC is 9.5, IB is 0.5. So 9.5 divided by 0.5 is beta is equal to 19. So current gain of transistor, given transistor is 19. Then move to next problem. A buck converter below, a buck converter shown in figure A is working in steady state. The output voltage and the inductor current can be assumed to be ripple free. So they were provided ripple free output and ripple free inductor current. Figure B shows the inductor voltage VL during a complete switching interval. Assuming all devices are ideal, the duty cycle of the buck converter is. So we want to calculate duty cycle of the buck converter. So here inductor current and output voltage is ripple free. Then they were provided inductor voltage with a complete switching interval. So from this given below diagram, average voltage across the inductor is 0, area under one cycle is 0. That is, so from this voltage we take it as average voltage across the inductor is 0. That is 3V into T on, that is 30 volt into T on minus 20 volt into T off. So the duration of 30, maximum voltage is 30 at the period of T on. At the period of T off, the maximum voltage is minus 20. So that is here 30 volt into T on minus 20 volt into T off, that is equal to 0. So we want a function T on by T off. So 30 divided by 20. Then adding 1 above the function. So we want to add 1 for duty cycle purpose. So T off by T on plus 1 is equal to 3 by 2 plus 1. It will be take common LCM, T off plus T on divided by T on, that is equal to 5 plus 2. So we want a function duty cycle D is equal to, or alpha is equal to, depends upon the denotation, duty cycle D is equal to T on divided by total time T, switching period T. So switching period means T on plus T off above. So above equation will be reciprocating. So T on divided by T, that is equal to 2 by 5. The final answer is 0.4. So this is final. Next, a steady DC current of 100 amps is flowing through a power module SD as shown in figure A. The VI characteristics of IGBT and diode D are shown in figure B and C respectively. The conduction power loss in a power module S and D is what? So what is the conduction power loss in a switches IGBT and diode? So this is the symbol for IGBT combination of diode circuit. So in this device VI characteristics they were provided. So the deviation of dV by dA is equal to 0.02 volt for IGBT. For diode dV by dt is equal to 0.01 ohm. So these characteristics we easily find out. The V naught of diode, that is equal to 0.07 volt, which will be less than the V naught of IGBT. Well, because IGBT have the voltage value of 1, it is much more greater than the diode voltage. So only diode will work, current will flow through diode only, and no current will flow in a IGBT. So therefore conduction power loss in a power module is PL is equal to 100 into 0.7, that is current, 100 of current, 100 into 0.7 plus 100 square into 0.01. So total power loss is 170 watt, 170 watt. Next, a single phase thyristor bridge rectifier is fed from a 230 volt 50 Hz single phase AC mains. If it is delivering a constant DC current of 10 amps at a firing angle of 30 degree, then value of power factor at a AC main is. So we want to calculate power factor of the AC main in a full single phase thyristor bridge rectifier circuit. So for a single phase thyristor bridge rectifier having the power factor formula of 2 root 2 pi into 2 root 2 divided by pi into cos alpha. So the constant will be calculated as 0.9. Cos alpha value they were provided firing angle 30 degree. So 0.9 into cos 30. So power factor is 0.72. So this is the final answer. So next problem. The switches T1 and T2 in figure A are switched in a complementary fashion with a sinusoidal pulse with modulation technique. The modulation voltage Vm of T is equal to 0.8 sine 200 pi t volt, and the triangular carrier voltage Vc are shown in figure B. The carrier frequency is 5 kHz. The peak value of 10 Hz component of the load current I in a amps. So we want to calculate load current in a circuit IL. So Vm is equal to 0.8 sine 200 pi t volt. Modulation index is 0.8. Then amplitude fundamental output voltage is modulation index into Vd by 2. Then peak value of 100 Hz component of load current with omega is equal to 200 pi t. So that is 200 pi omega. So high peak will be calculated as V peak divided by Z value. So V peak is 200, that is equal to R square plus XL square, that is equal to XL is equal to omega L square. It will be replaced as 200 divided by 12 square plus 16 square. So overall current is 10 amps. So this is the final answer for given problem. So this R and L value is taken from given load circuit. So next problem. The voltage Vs across and current Is through a semiconductor during turn-on transition are shown in figure. The energy dissipated during turn-on transition in millijoule is. So we want to energy dissipation in a semiconductor device. So they were provided characteristics of V and I with respect to time. So in this, energy losses during the time period T1 is calculated as 0 to T Vi into dt, that is equal to 600. Maximum voltage value is 600 at the period. 600 integral 0 to T. I is variable, but voltage is constant in this figure. So here 600 and I is variable. So 0 to T I into dt. Area under the T, it is little bit triangle shape. So that's why it is calculated as half BH square. So half into 150 into 10 to the power of minus 6. So the overall value will be calculated like this. So energy loss during the period T is 45 millijoules. Energy loss during T2, so this period 0 to T2 Vi dt, V value is 100, maximum peak V 100 into, that is I value is 100, V value is here change variable like this. Here current is same, but voltage is variable. So that's why 100 integral of 0 to T2 V into dt. So 100 into area under the curve, D2 is triangle of 600 into 10 to the power of minus 6, that is 1 millisecond they were multiplied. So 30 millisecond. Total energy loss is 45 plus 30 75 millijoules. So this is the answer for given problem, 75 millisecond. So next problem, a single phase full bridge voltage source inverter VSI is fed from 300 volt battery. A pulse of 120 degree duration is used to trigger the appropriate device in each off cycle. The RMS value of fundamental component of the output voltage in volt. So if we want to calculate the output voltage of the given VSI based single phase circuit. So for single phase VSI circuit having the output voltage 2 root 2 pi Vs sin D. Sin D is alpha is nothing but, so pulse width modulation 2D is equal to 120 degree. So they were provided 120 degree. For each and every half cycle it will trigger. So half cycle means it will be divided by 2. So 120 divided by 2, that is D is equal to 60 degree. So substitute here, V maximum is equal to 2 root 2 pi into V value 300. So 300 volt into sin 60 degree is root 2 by root 3 by 2. So overall function will be cancelled, 2 will be cancelled. So finally we got 234 volt. This is the final output for given problem. So these are the problems are asked in GATE examination 2016 relevant to electronic circuit and power electronics. Thank you. This video you like means share and subscribe my channel. Thank you.